Hello and welcome to Lecture 2 of our first unit of Intro to Music, the unit on elements. Last time we started out at the beginning with a definition of the word music, and then we started to talk a little bit about sound itself, how sound is created. I want to go back briefly to our definition of music, which, by the way, was music is the art of organizing or ordering sounds in time. I wanted to go back to it because I had two thoughts after I recorded that lecture, and one of them was I had seen a video on Facebook of Jerry Garcia, whom you may not have heard of, but was very big back in when I was your age. Jerry Garcia was the guitarist and sort of the central figure of the band The Grateful Dead. And this is a video that I saw on Facebook that had probably been made in the early 80s. And someone was talking to Jerry Garcia about rap. And Jerry Garcia said that rap is not music because it's just talking. Now, this is in the early days of rap. It was probably in the early 1980s. And this before rap really became as huge as it is now. And there were a lot of people who had this belief, so it wasn't uncommon at the time. And someone posted it on Facebook and kind of put the question out there like, is he right? Is rap music or not? And I answered, yes, it is music. Because in addition to the rhythmic speaking, which basically takes the place of melody, right? In more conventional types of music, I guess you have melody as sort of like the main thing that is out front that is supposed to draw your attention. In place of that, rap has rhythmic speech, but it does have other musical elements usually in the background, right? There might be some chords, there might be a bass line, there might be some kind of drums playing a beat. So it does qualify as music because there are sounds being organized for the purpose of sounds. It's just that the melody is kind of usually lacking pitches, we might say. It's spoken rather than sung. You might say, though, if we were to take those musical background elements out and just have like solo rap without anything else going on, then it maybe doesn't qualify as music anymore and becomes spoken poetry, which I talked about last time. The difference between spoken poetry as an auditory art form using organizing sounds and music. The difference being that in recited poetry, the sounds are not there primarily for the sake of being sounds. They're not to be experienced as sounds. They're to be experienced as encoders of meaning, the meaning that is in the words. There was another example that's kind of like pushes the edge of our definition of music that's mentioned in the book, actually, back on page 5 of the 2025 edition of the Camian text. They mention this piece by the composer John Cage. You may never have heard of John Cage, but if you have, it's probably because of his most famous composition, which is entitled 4 minutes, 33 seconds. That's the title of the piece, and it's a piece for piano. So if you were to go to a piano concert, a piano recital, and you grab your program from the usher and you sit down in your seat and you see that 4 minutes and 33 seconds by John Cage is being performed, you might see the pianist walk out, people will clap, he'll take a bow, sit down at the piano, maybe with a stopwatch, and do absolutely nothing for 4 minutes, 33 seconds. And then that's the piece. Then he would stand up and people would clap, maybe a little bit confusedly, and he would go on to his next piece. Now you might say, well, this doesn't really meet the definition at all because, number one, there's no sound. He's remaining silent for 4 minutes and 33 seconds. And if there's no sound, then there's no organization because music is the art of organizing sounds. I think John Cage, although he's hasn't been with us for about 3 decades or so, would respond something like this. He would say, actually, there is sound because even though the pianist is not playing, there's all kinds of background sounds. People will cough or sneeze or maybe unwrap those little crinkly mints that they bring with them. You might hear the sounds of a bus passing behind the concert hall or the sound of the ventilation system. There are going to be some sounds in there. They're random sounds, but that's the kind of sound that actually Cage was interested in. He was very interested in randomness, what he called chance music or aleatory music. And then you might reply, well, wait a minute, if it's random, then it's not really organized, is it? Random sounds shouldn't count as music. And John Cage, I think, would reply and say, well, they are mostly random, but there is some minimal organization being imposed upon these sounds. For one thing, look at the title, 4 minutes, 33 seconds. And remember, the most fundamental thing about a piece of music is time. And I have chosen this particular span of time, 4 minutes, 33 seconds, no more, no less. So I sort of bracketed time. The sounds you are hearing within those 4 minutes and 33 seconds, sounds which you otherwise might not have paid attention to because there would have been music playing, maybe sounds that you don't even pay attention to in real life because they're just background. He's kind of like forcing you to listen to these background sounds, but only for 4 minutes and 33 seconds. Cage might also say, I've also organized this musical event in the sense that I have brought all these people together in this room, maybe even sort of like from beyond the grave, because someone is performing my piece, a certain number of people gather in this auditorium, and certain sonic events happen during these 4 minutes and 33 seconds, which will never be repeated the exact same way again. Right? So it's unique. It's a unique performance. Every performance is special. So in that sense, there is some organization going on. Now, it is certainly the bare minimum amount of organization and the bare minimum amount of sound. So this is really at the edge of our definition of music, but I would argue that it actually qualifies. But I don't think you could really go beyond that and still have it qualify as music. Anyway, we arrived at a definition of music yesterday, and then I started talking about sound. Sound, of course, is caused by the vibration of some object. Those vibrations of the object itself are transferred to our ear through a medium, which is usually air. So the object vibrates. The air vibrates at the same speed. And our eardrum vibrates at that speed, and those impulses from our eardrum are picked up by the auditory nerve on the other side of the eardrum and transferred to our brain, and we perceive sound. I think where I left off last time was talking about the two most fundamental aspects of sound, which being a wave phenomena, those aspects are the amplitude of the wave and the frequency of the wave. So the amplitude is the amount of power, the amount of energy the wave has. And the frequency is how frequently in time are the waves like rolling in. And I use the example of waves on the ocean, right? You could go to the ocean and sit there with a stopwatch and measure how many waves per minute, let's say, came rolling up onto the shore. You could also go out there with a yardstick and measure how high the waves are, and that would be their amplitude. And they are two separate things. Same thing with sound waves. Now, sound waves are a little different from waves on the ocean because we can kind of think of the ocean as more or less a two-dimensional plane. And so the waves can only move in 2 dimensions. But with music, we have 3-dimensional pressure waves moving through the air. It's a little more complicated, but we can still use that sort of 2-dimensional model. Think of an X and a Y axis, right? And time is along one axis, this axis, and energy is along the other axis, right? Higher waves, more energy. More frequently occurring waves, higher frequency. Okay. I think I also mentioned that frequency is commonly measured in hertz, or cycles per second. And it is that number, that frequency, the hertz number, which determines the highness or lowness of sound. So the book has this heading, pitch, highness or lowness of sound. Remember, sounds are not really high or low. That's a space thing, not a time thing. Higher pitched sounds are not higher up, closer to the ceiling. Lower pitched sounds are not closer to the floor. It's just that the way that our brains work, we have a harder time. We're so used to the visual, which has to do with space, and so we use words that conform to that sort of paradigm of observation rather than what it really is, which is higher notes are caused by vibrations that are more frequent in time, lower notes by vibrations that are less frequent in time. Right? So it says here, the pitch of a sound is determined by the frequency of its vibrations, that is, their speed, which is measured in cycles per second. The faster the vibrations, the higher the pitch. The slower the vibrations, the lower the pitch. All other things being equal, smaller objects vibrate faster and have higher pitches. Thus, plucking a short string produces a higher pitch than plucking a long string. Well, why is that? The book doesn't really talk about it. I'm going to tell you why. Think of, again, the way that a sound wave works. If I strike some object or if I pluck some string, or in the case of, let's say, a wind instrument, if I have a column of air inside a tube that is this long versus a tube that is this long, right, it takes longer for the sound wave to travel the greater distance back and forth, even if it's going the same exact speed, than if the vibrating medium, the object that is struck, is shorter. Right? At the same speed, I can traverse that distance much faster. Right? If you think of a guitar string, now with strings, we also have to take into account the tension of the string. The higher the tension, then the higher the pitch will be because there's less resistance to the wave. So this is why when we are tuning a piano string or a guitar string, in order to make it higher, we have to increase the tension by turning that peg, and then we get this like until we get the right pitch. But if I have two strings of the same tension, but one is longer, one is shorter, the sound wave, sort of like the wave of people in a stadium, the bigger the stadium is, right? The people standing up and sitting back down again, the bigger the stadium is, it's going to take longer for the wave to cross it. Whereas if we have a shorter stadium, a shorter string, a shorter column of air, a shorter block of wood on a xylophone, if you ever noticed the blocks of wood on a xylophone or the metal blocks on a glockenspiel, these pitched percussion instruments, those blocks get shorter as the notes get higher, right? So that's the reason. The sound wave has simply less distance to travel. And this is why when we get into talking about the different families of instruments, the violin family, etc., the saxophone family is a good example of this. You have different varieties of saxophone, and the higher pitched ones are smaller, the lower pitched ones are bigger, although they otherwise look very similar to each other. Okay. And this gets into a discussion of pitch range. So the pitch range of any given instrument or any human voice is simply the total range from the highest to the lowest note that it can produce. Within that pitch range, by the way, we also sometimes speak of a register, the upper register, the middle register, the lower register. So register refers to part of a voice or instrument's overall range. If we're talking about human voices, we have some commonly used terms to describe these different ranges. And the four most common are, for men, the bass, then the tenor, and then for women, the lower is the alto and the higher is the soprano. So if you go and go to a choral concert, most choral music is written for SATB choir. Soprano, alto, tenor, bass. You have men and women. The higher pitched women are the soprano, the lower are the alto. Higher pitched men are the tenors, lower pitched are the basses. But we also have some in-between ranges, some extra ranges. So for example, between bass and tenor, we have baritone. Between alto and soprano, we have mezzo-soprano. Mezzo literally means medium in Italian. Hang on to that word. It's going to come in handy later. Mezzo. Sort of like a mezzanine. If you've ever been in a theater that has a mezzanine, you've got sort of the floor level, which is often called the orchestra. And then you've got a balcony, but in between you may have a mezzanine. It's in the middle. So mezzo means middle. We also might have extra low ranges like contrabass, below the bass. Contra means beneath or below. And again, those range names often transfer over to the instrument. So I mentioned the saxophone family. The very high saxophones are the soprano. Slightly lower is the alto. Then we have the tenor saxophone, baritone saxophone, bass saxophone. There's even a contrabass saxophone. It's like 8 feet tall or something. You don't see it very often. Anyway, so staying with pitches for a while, it might have occurred to you that there aren't really individual pitches in a sense, or let's say this, we have an unlimited number of pitches because we have a number spectrum, right, where there's a range. And yet, if you look on a piano, there are only so many pitches. If you look on a guitar, we've only got so many frets. If pitch corresponds to a number, well, there's really infinite numbers, aren't there? So, for example, remember last time I played this A, which is the note that you will hear an orchestra tune up to. This is commonly known as A440. It's the A above middle C on a piano, and it corresponds to 440 cycles per second. So if you have a digital piano, the computer chip can get it right on. If you are tuning a piano, you are trying as close as possible to get it so that, if you had a machine that measured it, it would perceive 440 cycles, that is, complete up and downs of the waveform in a second. Well, the next note up is not 441 cycles per second. It's not 440.1 or 440.001. I mean, we could make it that if we wanted to. We could mess with the computer in my digital piano. And on instruments that don't have discrete stops or keys or frets on a guitar, we can create sort of a continuum, sort of a slide effect, like on the violin. You sometimes hear this in maybe not so much in Beethoven or Mozart, but you will hear sometimes this sliding effect, which is called a glissando, maybe in movie music, and there are other instruments that can create this sort of pitch continuum. But in most Western music, we don't use the entire spectrum of pitches. We break it up into discrete notes, right? And maybe even more important than the notes themselves are the intervals. The intervals are the distances between the notes. Now, remember, they're not really distances because we're not talking about space. They are differences in frequency. They are differences in time from one note to another. So, again, an interval is a distance or difference in pitch from one pitch to another, right? So I'm going to spend a little bit of time talking about intervals. And I said intervals are actually more important than notes in a way. The way to think about this is one way to think about it is, imagine a connect the dots picture, right? The dots are important because otherwise you wouldn't be able to connect them to create the picture. But what's really creating the picture? It's not the dots, it's the lines that you are filling in between them. Something similar is going on in at least most Western music. Not necessarily all music of all different cultures, but certainly in Western music, and I think I can prove this, I might a little bit later on, that what you're really listening to is not the notes themselves, but the differences, the distances between the notes, the intervals. So intervals is a hugely important subject. If this was a music theory class, actually we would start out with intervals and I would be drilling you for weeks and months on intervals until you could recognize every different interval both on a piece of music immediately and also by ear. We'd be taking interval quizzes, right? You'd be memorizing the precise number of half steps in every different interval. So what's a half step? A half step is the smallest interval that is possible on most Western instruments, like the piano, right? So remember when I played this A, and then I went to the next highest note, which happens to be a B flat, that's a half step. If I do it down here, you might hear like the Jaws theme. That's a half step, repeated over and over again. And by the way, the direction of the interval doesn't matter. I could go from any given note down a half step, and it's still a half step. Directionality doesn't really matter. It's just the distance or difference in frequency, right? So the half step is also very easy to see on a guitar. It's simply, again, and now we are mapping this difference in frequency onto a physical object. So there is a space involved. We've got some space, and it's the space from one fret to the next fret. And again, it doesn't matter whether I'm going up or down. All right, that's still a half step. Now, what if I take a given note, I'll take this one, and I skip over one fret. I'm going to skip over this one, and I go to this one. That's called a whole step. So two half steps add up to a whole step. Okay? And again, it doesn't matter if I'm going up or down. Two half steps equal a whole step. The half step and the whole step are the two smallest intervals that are possible on the guitar, which has frets, on the piano, which has keys, and on other instruments that have some way of breaking down that pitch continuum into only the commonly used notes and intervals. Okay? And when we start in a theory class learning about other intervals, we always count the number of half steps that are in them, and we memorize that. For example, 3 half steps, right? So I'm going from our starting note, sort of like 0, 1, 2, 3. That's a minor third. Four half steps, a major third. And we would have to know the numbers of half steps. We'd have to memorize how many half steps in all of our different intervals. We don't need to do that for this class because this is Intro to Music and not music theory, but just to give you an idea of what's involved. Maybe the most important interval, other than the half step, I don't know, traditionally the most important interval corresponds to the simplest ratio. So all these intervals correspond to ratios, right? Because we have a number for a given note, a frequency, however many hertz, and then we have a number for whichever note is not the same note, that there's going to be an interval distance between them. The frequency of this note and the frequency of this different note could be expressed as a ratio. Ratios are hugely important in music. The simplest ratio is 2 to 1, right? And 2 to 1, the 2 to 1 ratio in music is called an octave, right? The octave is maybe the most important interval because it corresponds to the 2 to 1 ratio. Some of you are probably familiar with the octave. I'll play one first here on the piano. I'm just picking again my A440. There is an octave above A440. And guess what? That must mean that if this is A440, this is A880. If this is A440, then this is A220. This is A110. This is A55. And this lowest A, which is the lowest note on the piano, on most pianos, the lowest note is an A, 27.5. Now notice how this lowest A, it sounds a little growly, it sounds a little dirty, right? It's it's harder for us to get a fix on that, especially if I hadn't started out with all these other A's to provide a context. Like, okay, A, still A, but an octave down, A. Now, if I just started out with this one, you might say, well, I mean, it's a sound for sure, but I'm not sure if that's a pitch or not. And this is because human beings have a certain hearing range, as do other animals. And once we get too much lower than 27.5, what we perceive is kind of like noises or maybe vibrations, and they aren't really useful as pitches anymore. Now, there are a few custom pianos that have extra keys down there that sound even growlier and even worse. But I just wanted to bring this up because it kind of ties into sort of this interesting fact about the human hearing range. Human beings have a hearing range that goes from about, I think it's something like 20 hertz, 20 cycles per second, up to about 20,000 or so. Now that depends on your age, because think about it. The faster these frequencies are going, the faster your eardrum has to keep up with those frequencies in order to transmit those frequencies via your auditory nerve up to your brain. As you get older, the cartilage that your eardrum is made out of kind of stiffens and it can't vibrate as fast. And this is why when older people start to lose their hearing, what they lose first are those higher frequencies, right? And younger people can hear higher frequencies than older people can. Dogs and cats, we all know, can hear higher frequencies than people can. I have a cat that will sometimes meow to me like this. You can't hear it. You might have seen this, like cats that do this silent meow. Well, the cat doesn't realize that he's meowing to me in a frequency that I can't hear. There's another interesting thing about cats is the way that they catch mice very often is not necessarily by seeing them, but by hearing them, especially if they're scurrying around in the walls, or even if they're not scurrying around in the world. If the mice are talking to each other, because mice communicate with each other in frequencies that human beings can't hear, but that dogs and cats can. So if you've ever seen a dog or cat suddenly perk up and sort of start running after a mouse, it's because they heard a mouse that we can't hear. On the other side, by the way, whales and elephants, I'm told, can hear frequencies lower than we can hear. So they can often like detect an earthquake because they can feel the faintest waves coming up from the earth. They can hear them before we start to feel them as very intense, high amplitude vibrations. Anyway, so human beings have a certain pitch range, and on the piano, the lowest note that you see is getting down close to where our useful pitch range ends. And what we would perceive as sort of like rumbles and vibrations and maybe some noise, but not really a pitch. Okay, anyway, getting back to the interval of an octave, which I demonstrated on the piano, right? It's easier you can actually see the octave on the guitar fairly easily because it divides the string exactly in half. Now, the working length, the speaking length of a guitar string is from down here where it crosses this, I believe this is called a nut, where the string is effectively stopped. This part of the string is not really vibrating. It has to just kind of connect to the tuning peg. I mean, I could pluck this little tiny end, and it does produce a very high pitch. But the speaking length of the guitar string is from there up to the bridge. Remember, the bridge is where those vibrations get transferred into the body of the guitar, makes the air inside this hollow body start to vibrate and kind of projects it outward. So the sound is also stopped here. So the effective length of the string is from this white line to this other white line. And here's the string. If I pluck my low E string at its full length, there you can hear it. The octave fret on the guitar, the fret that I would push down on if I wanted to play the note that is an octave up, you might be able to see, and if you've ever noticed on a guitar, there's that one fret that has two dots on it. Well, it has two dots because it's the 2-to-1 ratio. If I stop the string there so that only this length, 1/2 of the string, is vibrating. I mean, this length is not really vibrating. This is the length that is vibrating over the amplification system of the guitar, the body, right? So this E is an octave higher than this E, because the sound wave, which, I mean, the tension of the string is the same, right? So we have a given tension, the sound wave is traveling back and forth, creating that note E. But if I cut the distance in half, now the sound wave, traveling at the same speed, only has half the distance to go. It can make the trip twice as frequently, and therefore the frequency is twice as high, right? So an octave is simply a 2-to-1 ratio. The octave, by the way, is also, as the book points out, the interval that you hear at the beginning of Somewhere Over the Rainbow, somewhere, right? Kind of interesting. It's a big leap, right? I forgot to point out, any interval larger than a step is called a leap, right? We have half steps, we have whole steps. Any larger interval than that, we can kind of sort of broadly categorize as leaps. The octave is a large leap. When we get to talking about melodies, we will talk a little bit about about the expressive properties of leaps. And I think in this case, somewhere, if you can sort of visualize it, somewhere over the, you get sort of a rainbow shape. Anyway, so getting back to talking about pitches and intervals, okay, you're probably somewhat familiar with the concept of a scale. Right? A scale is just a set of pitches that are usually separated from each other by whole or half steps. Some pattern, some combination of whole or half steps. Now there are some scales that have intervals larger than a whole or half step in them, but the two by far most commonly used scales use whole and half steps. And in a sense, you could think of a scale as not necessarily a set of pitches, but as an interval pattern. As an interval pattern that could be applied to a given pitch to get essentially kind of like the same logical result. It might be higher or lower, but the interval pattern is what one might say determines the scale. This is why I would say that, in a sense, intervals are more important than notes, at least in Western music. What you're really listening to in Western music, this might not be true of some other types of music, but in Western music, it's really the intervals that provide the meaning, such as there is, or that provide the information, more than the notes themselves. And this might seem kind of strange. It means you're not really listening to the notes. You're listening to the intervals in a way. Okay? This might seem kind of strange, but it's kind of provable. Because, for example, remember I was playing Somewhere Over the Rainbow, right? I could play completely different notes, but have the same intervals, and it would still sound good, right? It would sound like recognizable, like Somewhere Over the Rainbow. Right? Because I kept the intervals the same, right? You could do the same with Happy Birthday. I'm using completely different notes every time. But you recognize it as Happy Birthday because the information is bound up in the intervals and not in the notes. It's sort of like you could imagine a connect the dots drawing, right? What makes the drawing is not really the dots, but the lines between the dots. Once you fill in those lines, you get the drawing. Right? You could move the dots to a different place, but as long as all the distances between the dots were the same, you'd come up with the same drawing. Right? Anyway, let's check in on the book and see how far I've gotten. I've talked about intervals, octaves, pitch ranges, cycles per second. Right? I should also mention, in talking about ranges, the term register. Register refers to part of an instrument or a voice's overall range. So we speak of like the upper register, the lower register, the middle register. If your pitch range is thus, which again, here I am in space with high or low. It's not really. It's differences in frequency. It's a phenomenon in time, but there's no way of kind of representing that visually. So we have a higher register, a lower register, a middle register. All right, we will come back to talking about intervals, notes, scales, stuff like that, but I want to get too far ahead in talking about these are all aspects of frequencies, right? So remember, we have sounds, and sounds have an amplitude and they have a frequency. And so far I've been sort of talking just about the frequency aspects of sound, the high or the low, and the difference between two different notes, the difference in frequency or the distance in pitch. We call it an interval. We have smaller intervals that are called steps, larger intervals that are called leaps, one particularly special interval that's called the octave. But we're gonna hold off on going any further in that direction. We'll come back to that. Let's talk about the other aspect of sound, which is volume, the loudness or softness of a sound, which is determined by its amplitude. Right? And this is a term, dynamics, that we use to talk about volume. In classical music, we don't really use the word volume. We might in more popular types of music where you've got an amplifier, like turn down your volume. But in classical music, we use the term dynamics. Dynamics refers to the whole issue of loudness or softness in music. All right. And that, again, is a function of the amplitude of the sound wave, how much energy is being put into the wave. When a composer of classical music wants to indicate how loudly or how softly a performer is going to play, they typically use Italian words. Now, I should mention, composers didn't really start doing this until, I would say around the year 1700 or so, right? Before that, it was mostly just the pitches and the rhythms, the time durations of the notes that would be indicated. And things like how loud or how soft to play, that was just kind of left up to the performer to figure out on their own. But beginning in the 1700s, and certainly going into the 1800s, composers began being very specific in indicating how loud or how soft they wanted the musicians to play. And for various reasons, they all kind of settled on Italian as being the language for such indications. And Italian is the language that is used not only for indications of how loud or how soft, but also how fast or how slow one should play, and also just kind of like for indications of mood. If the composer wants to give you a sort of a hint of what kind of mood you should be projecting, they usually use Italian. So we're going to be learning some Italian here, right? In terms of dynamics, the dynamic markings on a piece of sheet music are based around two particular words, piano and forte. Piano means soft. You might think, oh, I thought the piano was a musical instrument. I'll get to that in a minute. It literally means soft. Forte means loud. And you might think, okay, well, forte, that's a term that I've heard before, like, I don't know, math is not my forte. Forte literally in Italian means strong, like a fort. Right? A fort is a stronghold. It is a strong place. But in Italian, when they want you to play sort of loudly, they tell you play strong. And over time, within a musical context, forte came to mean loud, but it really means sort of like energetically with strength. Piano means soft. And the reason that the instrument, the piano, is called the piano is because it was originally called the pianoforte, or sometimes the forte piano. It was called the loud soft, or the soft loud. And the reason for this is that the piano was the first keyboard instrument where you could control the volume just by pressing down harder or more softly with your fingers. It was the first touch-sensitive keyboard instrument, which the earlier instruments like the organ and the harpsichord were not. So when the piano was invented around the year 1700, the guy who invented it, Bartolomeo Cristofori, was Italian, decided to call it the loud soft, or the soft loud, or the keyboard instrument which can play both loud and soft. Okay, so piano and forte. Now, that doesn't give, loud or soft. What if we want medium loud or medium soft? Then we use the term mezzo. Mezzo means medium. Remember, I mentioned a mezzo soprano is between a soprano and an alto. Mezzo means medium or in between. So mezzo forte means medium loud. Not quite full-blown loud, but medium loud. Mezzo piano means medium soft. But what if we want to play really loud or really soft? Well, this is very handy in Italian. If you want to make an Italian word like really, all you have to do is add issimo on the end of it. So fortissimo means very loud. Pianissimo means very soft. Now, in practice, rather than write out all the letters of fortissimo or pianissimo or whatever, composers will usually abbreviate just using letters. So P means piano, F means forte, MP means mezzo piano, medium soft, MF means mezzo forte. If we want fortissimo, we write two Fs, pianissimo, two Ps. And in fact, if we want really, really, really loud, we could have three Fs. If we want really, really, really soft, three Ps. As many, some composers will write 4 or 5 Fs or Ps. Now, at a certain point, there's sort of a limit, but they're trying to emphasize, like, play this thing as loud as you possibly can. The more Fs there are, or as soft as you can if you see many Ps. Most composers don't go beyond 3 Fs or 3 Ps. We also have some terms for starting out soft but getting louder. That would be crescendo. You might think, okay, crescendo, it's just the Italian word for increase. Increase, crescendo. Crescendo means getting louder. Decrescendo means getting softer. De in Italian, it often means sort of like the opposite. So decrescendo means decrease instead of increase, right? Another word for decrescendo, by the way, is diminuendo. Sometimes we have more than one word for the same thing. Diminuendo. If something diminishes, it's getting softer. Diminuendo, decrescendo mean the same thing. And as the book indicates, and as I indicated here, we also have the possibility of writing in, instead of writing in the word, writing in something that kind of looks like a hairpin, going one direction or the other, to indicate whether over time, let's say the notes are up here, if we should get louder or if we should get softer. So, one other thing that they mention in this section on dynamics is something called a dynamic accent. An accent is indicated by a little mark above or below a note, and that is basically just telling the performer to play that note louder than the notes around it. So a dynamic accent is an indication that a certain note is supposed to be played louder than the note on either side of it. Okay, there's more to talk about with dynamics, but let's get to the final basic aspect of sound, especially of tones. And this is a very complex, mysterious aspect. that the book doesn't really get into that much on its own, but they do spend quite a bit of time talking about the different families of instruments afterwards. Anyway, this aspect of sound, of tones, is tone color, also known as timbre. Timbre. I know it looks like it should be timbre or timbre, but it's pronounced timbre. Timbre or tone color or tone quality all mean the same thing. Right? So if you see those words, timbre, tone color, tone quality, they all mean the same thing. What is timbre or tone color? It's basically that thing which enables you to distinguish between two different sounds produced by, let's say, two different vibrating objects, even if they are vibrating at the exact same frequency with the exact same amplitude. So for example, if I had over here a trumpet, and over here I had a violin, and I had an expert virtuoso trumpet player and violinist, and I had instruments around to measure precisely, and I said, okay, Mr. Trumpet Player, I want you to play A440 at exactly 70 decibels. Right? And I had my machines lined up, and he could see exactly, he could gauge his frequency to get it exactly in tune and gauge his amplitude, his dynamic level to get it exactly at 70 decibels. So we have an A440 at 70 decibels. I said, okay, good. We record that sound, and now I turn to the violinist and I say the same thing. Give me an A440 at 70 decibels. And he does it. We're going to be able to tell the difference between those two sounds. One of them sounds like a trumpet, one of them sounds like a violin, even though they have the exact same frequency and are being played at the exact same amplitude, as confirmed by the various sophisticated equipment I have set up. When you think about it, given what we know about sound waves so far, that should be impossible. Because a sound wave, all it has, right, is a certain frequency and a certain amplitude. Those are the only two aspects that we've talked about. And if the frequency and the amplitude are exactly the same, they should sound exactly the same. What else is there that could be different? Well, obviously there is something different, and you can intuitively know, well, one of them is made of metal and the other one is made of wood. One of them involves a column of air that is vibrating, and the other one involves a string that is vibrating and causing the wooden body of the violin to vibrate, and is also being initiated by drawing a bow across a string. So on an intuitive level, you understand why it is, but based on what we know about sound waves, why should that be possible, that we can have two very distinct different sounds at the same volume, the same frequency? That's what tone color is. And the reason for it is sound waves are much more complex than that simple picture. Think of waves on the ocean, right? You've got a wave on the ocean. But it doesn't stop there. If you were to look close up at the wave, you would see smaller waves that are riding along on that wave. And if you looked even closer, you'd see even smaller, like ripples on those waves. And if you were to keep looking, you would see ripples on ripples on ripples until you got down to the individual molecules, and then it would sort of break down. But there are many different sort of strata or layers of waves going on. And depending on the object which is doing the vibrating, the sort of the signature or the fingerprint or whatever of that waveform with all of its little particular ripples which are riding the main wave, it's going to be different from a trumpet to a violin. It's even going to be different from one violin to another. Now, we might not be able to tell, but an expert violinist who spends 6 hours a day playing the violin, they will prefer the sound of one to another, even though we might not be able to tell the difference at all. Even the type of wood that is used in two otherwise identical violins is going to be different, or guitars or something like this, right? Because each different vibrating material has its own sort of signature, its own pattern. Those little ripples that are riding on the main wave. Well, the main wave is called the fundamental. And the little ripples that are riding on that main wave are called overtones or partial tones. And again, they're sort of hierarchies of them. There are ripples upon ripples upon ripples. Now, those ripples obviously have much less amplitude than the main wave. And the higher up we go into the ripples on the ripples on the ripples into the higher overtones, the amplitude is very low. But you can still perceive them. And in fact, if we were to suddenly take them away and only have a fundamental tone, it would sound very strange and unnatural to you, because that's the way all objects in nature vibrate. They all produce overtones. Now, on a computer, we can generate a perfectly pure sound wave, and when we do that, we usually get something that ends up sounding like, those weird fake synthesizer sounds that we hear from like the 70s and 80s, The reason we can tell whether something sounds synthesized or fake is because the overtones are either greatly suppressed or they are forming a signature that we know just doesn't appear in nature. And we can tell that's a fake sound, that's a synthesized sound, because of that pattern of overtones. Anyway, it is this unique signature of overtones, of these tiny little ripples riding on the main wave, the differences in one material or one means of producing sound, like blowing air through a metal tube, or getting air to vibrate inside a metal tube, and drawing on a string that is attached to a wooden instrument. That's what causes differences in tone quality or timbre. And what this leads to, which I'm not going to get into now, but we'll get into in the next lecture, is a discussion of the different families of musical instruments. Since we have this possibility, thank goodness, it's not the case that a violin and a trumpet are going to sound identical. There wouldn't be any point in having different musical instruments if we didn't have this property of tone color. And this is something that musicians and composers love to exploit. It's like they have a palette of all these different colors before them that they can combine and use in different ways. Some composers are particularly masterful at that, at exploring that aspect of music. Others are less interested, actually, as we will see. But what we will do in our next lecture is talk about the various families of instruments, and we're going to break them down into stringed instruments, wind instruments, percussion instruments, and also some categories that don't really break down the same way, like keyboard instruments. If we're talking about string instruments, the string is actually the origin of the sound. If we're talking about wind instruments, the wind, the air inside of a tube of some kind, is the origin of a sound. Percussion instruments, we are percussing, we are hitting something. And when that object starts to vibrate as a result, that is the source of the sound. But a keyboard instrument, on a keyboard instrument, the keyboard is not really the source of the sound. It's just like the user interface. It's the controller. And the sound could be produced in many different ways, actually. And then we can also get into electronic instruments. We'll talk about those a little bit, but we're going to be mainly concerned with the traditional instruments of Western art or classical music. And we're going to break them down and organize. There's a lot of instruments. We're going to try and break them down and make them easier to get a handle on. We'll separate them into their different families and also sort of separate them vertically by their ranges, by their pitch ranges. So that's what we'll do next time. We'll have a discussion of musical instruments. See you then.